Okay, so now it's recording. Good morning, everyone. Welcome to Lecture 8 of the course Quantum Theory in a Nutshell. So today I want to discuss with you a very particular system. And with this system, I will introduce some general concepts of quantum mechanics and also start introducing some notation that is very important in quantum mechanics. But before I start with the polarization of light, which will be the phenomenon that we are going to discuss, let me remind you that yesterday we discussed the double slit experiment, and what we did was to analyze it with classical waves, classical particles, and then with electrons. And what we have seen is that, just to make the picture coherent, is that waves, when they cross the double slit, what they screen with two slits, the wave is a delocalized object, so it passes through the two slits, and after that, the slits will act as primary sources of the waves, and the new waves will interfere with each other in such a way that on the second screen you see an interference pattern. So you remember that we had these bright and dark fringes, um, um, and what we um, what we have discussed is that in order to describe mathematically this phenomenon, we needed to use the concept of a wave function, and the interference is accounted by the fact that in order to compute the intensity on the second screen, you don't simply add the intensities uh, for the case where one slit is blocked, and then you block the other slit and open the first one, and then you don't just simply sum the intensities that you see in this situation. You have to add the wave functions and then compute the intensity. And this makes a lot of difference, because when you add the wave functions, you can have constructive or destructive interference, and this is very important. Okay, um, so I want to emphasize that this is different from the situation with classical particles, where the very fact that particles will go through one slit or the other slit, so a particle will choose which slit it is passing through. Um, if I make the rate of shooting the particles slow enough, I can be sure that I will have just one particle crossing the screen with the slits. And what we saw is that the chances of getting the particle in a given region of the second screen are such that you simply add the probability distributions of the independent events when you block one of the slits. So if you block one of the slits, you get a probability distribution, and if you block the other slit, oh, sorry, there is a microphone open.
Mahmoud, when your microphone is on.
Okay, so there is let me check. There is something in the chat. Uh, so yeah, my throat. Well, yeah. So it's better. It's getting better. So it's just because it's cold here. Um, okay, so um, okay. Now let me continue with the discussion. So we saw that when you are talking about classical particles, you simply add the independent probabilities of a particle to cross one of the slits, and it is different from the waves because you simply add probabilities instead of computing the interference pattern. So what you see when you have a bunch of classical particles crossing the slits is a pattern that you have a concentration of particles in the region in front of the slits, and the chances of getting particles away from this region is much lower. So you see less particles. So there is a question in the chat. Is the effect of measurement? So actually, the way that you the thing that you're asking, which is about the measurement that I'm going to get there. Yes, it is Compton scattering. Yes. Okay. But we saw that classical particles and classical waves behave very differently when they are directed to a screen with two slits. But now, if you repeat the experiment and you throw a beam of electrons, what we have seen is that if you uh, um, start throwing the electrons against the two slits in the beginning, so this is an accumulation effect. So in the beginning, you're going to see more electrons concentrated in front of the slits, and then you're going to say, aha, the electrons are particles. But then, if you wait long enough, you are going to see that actually the electrons appear as a wave pattern. So there is the interference um, um, pattern of a region where you are going to see that electrons arrived, a dark region where electrons didn't arrive, and again a bright region, and so on and so forth. So the electrons, they pass through the slits and they interfere, so that there is a superposition in such a way that you're going to see this destructive or constructive behavior. And because of that, we decided to introduce a wave function that is associated with the electron, and we call it psi. And as we discussed, now that you have a wave function, you can describe the electrons by using the same language that you use to describe waves. So if I want to compute the probability distribution of getting the electron in a position X, then I have to add these wave functions as you do with a wave, and you square that. So this is really um, um, the introduction of a mathematical object, which is the wave function for the electron, in such a way that when you add these things and the square, you get a quantity that is related to the probability of finding the electron in a given region of the second screen. So you're seeing that I have introduced the wave function as something that is a mathematical device to reproduce the results that I see in the experiment. Okay. Many people try to give a physical meaning to the wave function, namely, really think about a physical wave that propagates in space. And this is it's a very complicated way of seeing the wave function. And if you take seriously that the wave function is a real entity, is something that you should, I mean, in quotation marks, see propagating around, then there are many difficulties with that. So for us, and also to keep the discussion down to earth in the first approach, I want you to view the wave function as a mathematical device that helps you or tells you how to describe the wave behavior of the electron, okay? And then we moved to this discussion, which you probably also watched in the video that I posted yesterday, that if you if you decide now to detect from which slit the electron is passing through, because if you insist that electrons must behave as particles, then they have to choose if they pass through slit 1 or if they pass through slit 2, because particles are localized objects, so they cannot pass through the two slits simultaneously. So when you detect from which slit the electron is coming from, for instance, by just directing some radiation light towards the slit, you see that the electron will interact with the photon that you send, and it will emit, it will scatter actually radiation that you detect. So this is essentially the Compton scattering, as Mahmoud said, and you detect and you can tell if the scattered radiation is coming from slit 1 or if it is coming from slit 2. And then you just stay there looking at the electrons and you just take notes. I mean, electron 1 came from slit 1, electron 2 came from slit 2, electron 3 came from slit 2, and so on and so forth. And when you turn your eyes to the screen, to the second screen, to see what you would expect as the interference pattern of a wave, you see that they appear as particles. So they appear with a pattern that you see for particles. So you essentially destroy the wave behavior of the electron when you detect from which slit the electron came from. And so Mahmoud is asking if the measurement was made. So the measurement is made on the two slit. So you can precisely, every electron that cross this region, you can precisely tell if it came from a slit 1 or from a slit 2. Okay. So what we saw is that the measurement itself affects the system and changes the outcomes of the experiment. And we had a discussion about that in the sense that, I mean, the same is true in classical physics, but of course, when you go down to the microscopic scales, not a very tiny interaction with the system might be enough to change completely the system itself. So um, this tentative of really making the effects of the measurement very small so that you don't change the system is very tricky at the microscopic level. For instance, you can say, well, if I want to make the effects of this measurement small enough, I can reduce the energy of the photon, okay, so that the energy carried by the photon is not high enough, and I don't affect too much the electron. So you start reducing the energy of the light beam that you're sending towards the electrons, and the energy is getting lower, 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 and at some point it is so low that you are going to see again the wave interference pattern, because the measurement is affecting less and less the system. But the problem is that when you reduce the energy that the photons are carrying, you're going to have so small energies that the corresponding wavelengths of the photons will not be detectable by any detectors that we know. So if you reduce the energy of the photons too much, then you cannot tell from which slit the electrons came from. So it's really a conspiracy that does not allow you to say if the electrons came from slit 1 and 2, and at the same time have the wave interference pattern. So it's really a very non-trivial and very counterintuitive effect. But of course, you don't have to expect that your intuition will be valid in the microscopic world. I mean, your intuition is constructed at the macroscopic level. So we are used to scales that are way higher than the scales of an electron. So there is no reason for nature to work as you would guess in the microscopic level, because you don't have any intuition in this region. Okay. And then we saw that, I mean, there is a precise meaning for the square of the wave function, which is given by what is called the Born rule, or um, the the relation of the square of the wave function times dx gives you the probability of finding the particle in the region between x and x plus dx. So this is really what we are learning for quantum theory, which is quantum theory will make us be able to compute probabilities. So you're going to compute the probability of getting an electron in this region, but you're not going to be able to compute um, um, the exact position of an electron after passing through the slits. So you're going to compute the chances of finding an electron in a given region. Okay, that's very different from Newtonian theory, because Newtonian theory is completely deterministic. I mean, you you have a particle that moves according to Newton's law, and if you know all the forces that act on the particle, you have that the total force is the mass of the particle times its acceleration. So this is a differential equation that you can solve in principle, and if you solve that, then you're going to have the position of the particle at every instant of time. So you can really say that when I see my clock and I see that it's, I don't know, 8:30, I will tell you where the particle is with respect to some reference frame. And quantum mechanics is not about that. So if you want to know what is the if you want to know information about the motion of a particle, you're going to say that the probability of finding the particle in such a position is, and then the number. Okay, so quantum mechanics is about that, and we are going to start looking at a system, which is, as I said, is the polarization of light, where this is a very simple system, and therefore, I mean, because it is simple, and by simple I mean that you have you need few parameters in order to describe the system. Then the quantum version of that will also be simple. Okay, so it's much simpler than than describing what is the position of a particle, because in principle a particle can be in whatever place in a continuous amounts of places. So the polarization of light is much simpler, and I'm going to explain why. So there is something in the chat. Let's see. And for the mesoscopic level, You mean about your intuition at the mesoscopic level, or am I making some confusion? Yeah. So um, I don't think you can say that you have an intuition there, but yeah. But so it's I'm not so sure if you can say that your intuition will be a very good guiding principle there, because there are effects at the mesoscopic level that you could not guess from your intuition. So, but of course, I mean, as soon as you depart from the deep microscopic level, your intuition starts to become better and better, let's say, tool to guide you. But also, let me say that even for macroscopic systems, there are situations where our intuition just fail. I mean, and you don't have to trust. I mean, as a physicist or as a scientist, uh, of course, having a good intuition can inspire you in order to, you know, um, 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 get more information about the system, or telling you what is the direction that you should go in order to find some information about the system. But you don't have, or you should not trust your intuition in order to describe physical systems in general, because sometimes intuition fails, and as a scientist you want to predict things without, let's say, any doubt. So if the theory that you have to describe some phenomena is at work, then you just compute and tell people what is the result. Okay. But of course, I mean, there are many situations where you just guess what is the answer based on your intuition, and it works. Okay. Good. Okay, so let me start the discussion of polarization of light. And as I said, this will be an environment where I will introduce the formalism of quantum mechanics. Okay, so as I discuss about this system, I will introduce you some rules and some notation that will be used in quantum mechanics when you want to describe a more generic system. Okay. Okay, so at the classical level, if you want to describe the polarization, and I'm going to explain to you more what I mean by that, of a monochromatic. So when I say that, I'm saying that the light that I am studying is of a single color, which, as we have learned, is related to the frequency, or if you prefer, the wavelength of light. So when I say monochromatic, I mean that I have some light beam with a well-defined frequency or wavelength. So I don't have a superposition of several different wavelengths and frequencies. Okay. So at the classical level, if you want to describe the polarization of monochromatic light, you just have to know two parameters, okay? And these parameters are related to the amplitudes of the electric field in two orthogonal directions, and the phase shift between this electromagnetic electric field, because light, as described by Maxwell, is a wave made of electric and magnetic fields that are oscillating in time. So there will be one component of the electric field that will oscillate, and another component that will oscillate with some a phase shift with respect to the other component. And this is the information that you need. But of course, so let me just explain to you what I mean by this drawing. So these circles here are the polarizers. So they are the device that polarize the light ray that you direct against it. And you see that, so I have an axis here that I label by X. So this green axis is just a fixed direction that I use as a reference. So this is one polarizer, and I have this preferred direction here. And I can, so the polarizer have essentially, so it has essentially a place that is opened where I can make light pass through. So if I want to pass light through this polarizer, there will be a direction theta. So this direction in gray here is the direction of this polarizer. And when I pass through light here, I say that light is polarized in the theta direction. Okay? So if I have some light coming in with an intensity I naught, then I will have light coming out with some intensity I, which is different from I naught, because part of the light will be absorbed by the polarizer, where part of light will just pass through this axis, this gray axis. Okay, and I can rotate the polarizer, so I can have a second polarizer that points in a different direction that I am calling phi. And when light passes through the polarizer with polarization phi, I say that light will be polarized in the phi direction. Okay, so this vector k represents the direction at which my light wave propagates. So I'm talking about monochromatic light that is that also has a well-defined propagation direction. There is a question in the chat. Let me. Is it a device? Yes. So the polarizer, you can think of it as a disk with, you just open a thin slit on this disk, and when you pass light here, so the electric fields that are not aligned with this direction, they are going to be absorbed by the polarizer, while the electric field that oscillates in this direction will pass through. Okay, so you're going to, after passing light through the polarizer, you're going to have an electric field that has a well-defined oscillation direction. Okay, which is the direction of your polarizer. Okay. Okay, so when I talk about waves and electric magnetic waves, and I'm talking about a field that is going to hit the polarizer, I can think of an electric field that is very complicated, so it has components in different directions. And when I throw light against the polarizer, the component in this direction will pass through, but the other components will be absorbed. So it's easy for me to explain that as part of my electric field, namely the component in this direction, is going to pass through the polarizer. So I can say that my electric field, my initial electric field, is partially absorbed by the polarizer, but also partially transmitted. Okay, so this is not a problem. I can think about an electric field that has some components that will be absorbed and some components that will pass through. But now, okay, so what is the aim of the polarization of light? Is precisely to, have a well-defined direction of oscillation of your electric field. Okay, so if you want to, for instance, if you want to use light to start oscillating a particle with an electromagnetic wave, you can use a polarizer to make the electric field well-defined and just oscillating in one particular direction. And when you throw this wave towards a particle, the particle will suffer an electric force in the direction of this electric field. So you can really um, yeah, I'm talking about monochromatic light. Yes. Okay. Good. Is that yes? So this polarizer, it can be a material that has some properties in such a way that you can absorb electric field, but also reflect some part of the electric field. Yes. Okay. Good. So now I want to describe the polarization of light as a beam of photons. Okay. We know that when light interacts with some material, so when we threw light against a metal plate, it was behaving as a beam of particles. Okay. So if I want to describe the interaction of the light with the polarizer as a beam of photons, how do I explain that? And this is something that um, immediately brings some confusions. Okay, so to begin with, when I throw photons against this polarizer, there are two options. Either the photons will pass through, or the photons will not. So there is no such a thing of passing half of a photon. Okay, so if I send a beam of photons, I have to tell you whether the photon passed through or if the photon did not pass. Okay. Moreover, I have to be very careful with the fact that when I send a beam of photons, I take photons as being identical particles. Okay. So if you think classically and you're sending identical particle against a target, then you can think, well, what happens with one of them, it is what is going to happen with all of them. Because there is no reason for, if the particles are identical and are sending an identical coherent beam, there is no reason for one particle behave in a way that is different from the other. And there is a question in the chat, which is, what do you mean by identical? Well, I really mean that if I have two photons in this beam, I cannot distinguish them. Okay, I cannot look at this photon and look at this photon and tell that they are different. They have the same properties. Since light is monochromatic, all the photons will have the same energy because the frequency is the same. So I cannot differentiate these photons in this beam. Okay. So the thing that I want to describe is the following. I want to pass through light against the first polarizer, then some polarized light will come out, and then I will place another polarizer, okay, and um, and I want to look at the final beam of light that appears after the second polarizer. Okay, so let me tell you one thing. If the first polarizer is in the direction theta, and the second polarizer is also placed in the direction theta, this is what you observe. I'm going to tell you the result of an experiment. If I throw light of intensity I naught, it will pass through this polarizer and it will have some different intensity I. And if the angle here is also theta, then I will see the intensity of the light after the second polarizer as being identical to the intensity in between the polarizers. So if I have angle theta, and I place this polarizer with angle theta as well, I see no difference in the intensity of the light in this region and the light in this region. Okay. Another outcome is the following. If now, so if I place this first polarizer in the direction theta, and I come here and I rotate this polarizer to form 90 degrees, so pi over 2, with respect to theta. So I start here with theta, and then I just rotate 90 degrees. So this polarizer has a direction which is orthogonal between with respect to this polarizer. Okay, so I'm describing to you now the outcome of an experiment. If I throw light with intensity I naught, it will pass through the first polarizer, and it is going to have an intensity I in this region. And now the second polarizer is placed with a direction of 90 degrees with respect to the first one. And what you see here is that the intensity goes to 0. So if the polarizers are orthogonal, then no light will escape to this region. Okay? Again, if phi is equal to theta, then you see no change on the intensity in this region and this region. If phi is orthogonal to theta, then you see no light in this region. So, summarizing, if the polarizers have the same direction, then light, after passing through the first polarizer, will pass through the second polarizer as nothing happened. I mean, it's going to pass through and have the same properties that it had here. But now, if I rotate phi in such a way that it is orthogonal with respect to theta, what I see is that the light that is here, when passed through the second polarizer, is completely absorbed. Okay, so I don't see light here anymore. Okay, so let me go to the chat before I continue. So is there, Mahmoud asked, is there a relation between theta and phi? So in principle, theta and phi are independent angles that you choose. Okay, so you can choose phi completely different from theta, and it's just an experimental choice. Okay. So typically, if you want to test, for instance, if this polarizer is good, then you pass light through this polarizer. You now place a second polarizer in the same direction as this polarizer, and check if the intensity of light that is going out is also is the same as the intensity that you would see here. So this polarizer, in a sense, analyzes if this first polarizer polarized light properly. Okay. If there is no difference, why to use two polarizers? Yeah, so I'm just explaining facts of the experiment. So if you just place the second polarizer in the same direction of the first polarizer, you're going to see no difference. So the usefulness of that is the one that I just mentioned. You can test, because when we are talking about real experiments, the devices that you use are not perfect. So you better check if your polarizer is working. So this is a way of testing that. Okay. And Silas asked, is the mathematics to explain this concept? Yes, yes. And this is what we are going to develop. Okay. Okay. So let me check if I said everything that I wanted about that. Let's consider light. Okay. So let me move to the next slide. Okay, so first I want, if you didn't learn that before, it's easy. But if you learned, I want to remind you that when you analyze the polarization of light using classical electromagnetism, you know how to compute the intensity. So if I want to compute the intensity of light here, and I know the intensity of light here that I call I naught, I know how to compute I with the information about I naught and the angles of the polarizers. So the resulting intensity, so the intensity of light coming out from the second polarizer will be I naught, which is the intensity of light before crossing the first polarizer, times the square of the cosine of the difference between theta and phi. Okay? So you see immediately that if phi is equal to theta, then you have cosine of 0, cosine squared of 0, which is 1. So I is equal to I naught. So if the polarizers, um, um, they have um, um, uh, the same direction, then light will come out as it entered. Okay. Uh, However, if the angle, the directions of the polarizers um, is such that theta minus phi is plus or minus pi over 2, then what happens is that um, theta minus phi is going to be pi over 2 or minus pi over 2, and cosine of pi over 2 or minus pi over 2 is 0. So the intensity I is going to be 0. As I said, if the directions of the polarizers are orthogonal, then the final intensity is simply 0. Okay? Um, Good. Um, Someone asked, why cosine squared? Yeah, that's an interesting question. You can work out why it is cosine squared, but for the moment, I'm just going to declare that this is cosine squared. But there is a nice way of showing that. Okay, that maybe I can explain to you, or even write as an exercise. Okay, good. Okay, so as I said, uh, the polarization, as I described, is a particular type of polarization that is called linear polarization. So the polarizer is pointing to some specific direction, and it is going to let the electromagnetic wave pass through with electric field that oscillates in the direction of the polarizer. Okay, so this is a very important concept. I'm talking about, now that I have introduced all these concepts, I can tell you that I am considering the linear polarization of monochromatic light that travels in a fixed direction. So this is a complicated name, but this is what it is. Okay, and I hope that all the words that I said now are understandable for you. Um, okay, so let me just let me just recap the setup. I throw some light, and it passes through the polarizer and has some intensity I, and this light with intensity I will just go through the second polarizer, and sorry, I'm using the wrong name. So if I send light through this polarizer, it's going to pass through it, and it will be polarized in the theta direction with intensity I naught. And then it goes through the second polarizer with direction theta, and it is going to get out with polarization phi and intensity I. And the relation between the intensity here and the intensity here is such that the intensity here is equal to the intensity in this region times cosine square of the difference of these angles, okay? So now, again, we want to describe photons. So when I pass light through the first polarizer, in the wave picture, I say that the electric field is oscillating in the direction of theta. So when I think about photons now, when the light beam just passed through this polarized, I will introduce this name. I'm going to say that the photons, so the light that is here will be composed by photons that are polarized in the theta direction. This is a name, okay? I'm just saying that I'm going to call the photons in this region as photons that are polarized in the theta direction, okay? And so let me go to the chat because there are some questions. In the second, okay, so sorry. Please, can you repeat when the angles are not equal? Okay, so if theta and phi are not uh, equal, then the intensity of the light that is going to go out of the second polarizer is given by this expression, okay? So cosine squared is a number that is between 0 and 1, right? So what you can say is that the intensity I after the second polarizer will be equal or is smaller than I naught, okay? And the minimum is I equals to 0, and it corresponds to the situation where theta and phi are orthogonal angles, okay? I hope this answered the question. Then, John, in the second polarizer, what is the intensity? Is it not okay? So after the second polarizer, okay, so I'm shedding some light here towards the first polarizer with some intensity that I don't know, okay? And then it passes through the first polarizer, and it will have some intensity I naught that I measure. And after passing the second polarizer, it is going to have intensity I, okay? So the intensity after the second polarizer is I, but it's not a random number, but it's related to I naught by the cosine squared of the difference between theta and phi, okay? Eugene asked, what is the intensity of light passing? Okay, so light that is coming here has some intensity I prime that I don't know, okay? So the intensity that matters is the intensity after the first polarizer, which is I naught, and the intensity after the second polarizer, which is I, okay? Do you understand? And what is written here is that the second polarizer will just permit that a fraction of the intensity of the first after the first polarizer will pass. So as you see, I is equal to I naught times cosine squared. And since this number is between 0 and 1, we say that just a fraction of I naught will go through. Okay? And then Mahmoud said, why we are interested in the electric field only? What about the magnetic field? Well, that's a good question, but the electric field is related to the magnetic field by Maxwell's equation. So if you know how to describe one, you can use Maxwell's equation to describe the second one. Okay, so you don't have to. This is not an independent construction when you are talking about light waves in vacuum. Okay. So if you have knowledge about one, you're going to have knowledge about the other. Okay. Okay. So I want now to turn this discussion to photons. Okay. There is another question. Sorry. When will I? So I is not greater than I naught. Never. I mean, I is always equal or is smaller than I naught. Okay. Because it is multiplied by a number that is between 0 and 1. Okay. Good. Okay, so I want to move the discussion now to photons, but it's better if you have the break in order to not be interrupted in the middle of the explanation. So we stop for 10 minutes and we see each other again to discuss these properties that I just mentioned, but thinking about photons, okay? So see you in a bit.